I'd like Chris Deacon from the University of Bath, G4IFX, to get ready. And before he presents, just a quick message. We did hear back from Mark Driscoll in Antarctica. Everything is well, and he's even started creating an Antarctica rural group on Facebook. So he's all okay. Go ahead, Chris.
Hi, everybody. It's Chris here. Yes, how do I follow that? I don't know. I'm going to be talking about something that's actually a lot more common than long delay echoes, sporadic E. But before I say that, I've been licensed since I was 16 years old. So you can work that out for yourself. But now I'm a student again. I'm working towards a PhD. I've been for the last part-time for the last 2.5 years with Catherine Mitchell at the University of Bath, and oh, there we go. So I'm not going to be talking about how sporadic E is formed, when it occurs, or any of the other interesting stuff that I'm sure will be covered on the tutorial tomorrow. A question that's puzzled me for quite a few years is actually what happens when the wave is reflected by the sporadic E. A lot of people will just think of it as being like a mirror. Other people refer to it as being some sort of scatter, hence the sprinkles, or hundreds and thousands as we call them in England, or it's just boring old, same old magneto-ionic propagation, just like the rest of the ionosphere. But even if it's that, sporadic E is different. It's formed by a different mechanism. The ionization is very intense but very thin, and that's likely to change. To me, right from the start, it was likely to change what happens in a qualitative as well as a quantitative way. And the polarization state of the reflected wave, I think, is a key mechanism, a key way to find out which of these it actually is, because a mirror will just reflect a linearly polarized wave. It'll be linear, it might be tilted a bit, but it'll still be linear. Scatter, the same, except that when the reflection points are very, very small, it'll tend to be depolarized completely, and magneto-ionic, it'll be elliptical. So here's just a representation. I'll return to this picture representation at the end, but there's a couple of important points here. Firstly, a linearly polarized wave, let's assume it is linear, as it enters the ionosphere, cannot propagate in the magnetized plasma, as we've heard a couple of times already today. It splits into these ordinary and extraordinary waves. They have opposite senses of rotation. They are elliptically polarized. There's some sort of change on reflection at the top there. By the way, that symbol there, the little arrow, is approximately the thickness of a typical sporadic E layer, a couple of kilometers. You can see it's pretty thin. I happen to have represented this one at 100K. The downward wave will definitely be elliptical. The polarization will probably continue to change, although not necessarily very much once it gets out of the sporadic E, because I'm talking here about 6 meters, I'm talking about 50 megahertz. And there'll be a combined wave with elliptical polarization. That's the hypothesis that I've been sort of setting out to test. So here's the experiment. I will explain, actually, I should have put a slide into this. I'm going to talk about how I collected the data and analyzed it up to a point, because it's all been written up in that paper. I'm going to talk about an overview of the results to date, then look at some modeling that I've been doing, having established some basic findings to see if I can actually reproduce the kind of effects that I'm seeing by ray trace modeling in FARLAP. So the experimental campaign took place in the summer of 2018, between about May and about August, monitoring beacons, amateur beacons, not in my control. They just spread across Europe. There are actually a lot more than show up on this chart, and I got decent data from half a dozen of them, and I'll talk a bit more about that shortly. Using a fairly big 6-meter antenna, 7 element at 18 meters above the ground, but cross-polarized on a single boom, into a dual channel synchronized SDR receivers with a calibration capability, and that just captures INQ data at some fairly high sample rates, so 6,000 or 24,000 kilohertz samples per second, in other words. And then the clever stuff really comes in the analysis of that. You have to find the useful data, because sporadic E is very intermittent. If you just sit a transmitter somewhere and sit a receiver somewhere, you'll probably wait quite a long time before there happens to be an opening, a 6-meter opening between those 2 points. So you need to sort of be monitoring widely and finding the signals. You separate out the beacons, filter them, measure the calibration values. We've also compensated for phase change and amplitude change on reflection from the ground, because the vertical and horizontal components are affected differently. And then you can use that information to, for instance, calculate, well, you're actually measuring the amplitude difference between the horizontal and vertical components, and the phase difference between the horizontal and vertical components. And then you can also calculate other things like what the shape of the polarization ellipse actually is. So I can answer more questions about that later if you want, but as I say, there's a lot of more information in the paper about that, and I think Ben Whitfleet may well be on the call, my main sort of co-author there, and in fact I think he drew most of these diagrams. So here's a summary of the results. And I'm just going to close this window so I can actually see my whole screen. Yeah, so I've got results here from the Faroes in the north to Spain in the south, across to Hungary and Slovenia in the east. And there's it's actually all done from my home. So the general pattern is that. And I deliberately did this, by the way, because I wanted to be across and a parallel to the Earth's magnetic field, roughly. And generally speaking, the north-south paths are more unstable, and the east-west ones are relatively stable, which is why I've spent more time looking at them. But also, there's a sort of a systematic difference. I don't know if you look around here: Hungary, right hand; Slovenia, left hand. They're all elliptically polarized consistently. It might swing through linear or circular, but it's all elliptically polarized to one degree or another. But Hungary and Slovenia are actually not very far apart, but one comes down consistently on multiple days, right-hand elliptical, the other one comes down on multiple days, left-hand elliptical. And then you sort of work your way around this, and there's an Italian one, and left hand for this one here. Now, the only consistent pattern that I can see, and I can't explain this yet, is that all the ones that are coming up as left-hand elliptical are inside this circle. They're inside the 1400. I mean, I don't know if it's 1400 or 1350 or 1450, whatever. But an arbitrary 1400 kilometer circle. They're all inside it, so they're all at shorter distances. Maybe that's something to do with it. I don't know. So I've decided to spend more time looking specifically at the Hungarian and Slovenian ones. As I say, they're both on similar paths, and yet they have a very dramatic difference between them. So here's, this is actually real data, by the way. It's not a simulation. It's drawing the polarization ellipse it's actually doing it 25 times a second. And you can see that on this particular day, and in fact it was fairly stable on most of the days, the signal from the Hungarian beacon was fairly consistently strongly elliptical and tilted up into the top right-hand quadrant, if you like. And it's right-hand. Blue on this chart is right-hand circular or right-hand elliptical polarization. Whereas the Slovenian beacon, similar strength, in fact, actually stronger signals from Slovenia. And I picked one here that is actually showing some disturbances as well. So you can see the polarization rotation that happens, but it's consistently left-hand. There's a sort of a home polarization, which is consistently left-hand circular, left-hand elliptical, and it's in the top left-hand quadrant of the square. Now that's very interesting in itself, because it actually contradicts some things that you would read if you read some of the textbooks. But we'll get to why that might be, perhaps. Now, next I need to introduce you to, just because it's such a useful way of representing polarization states, something called Poincare Sphere. I'm going to share that, and the reason I do that is it's a three-dimensional thing, three-dimensional representation of the polarization state of a wave. It's generally used in optics. It was one of the thousands of inventions of the mathematician Henri Poincare, I don't know, 120, 150 years ago. But it very quickly points out the key visualization tool, if you like. And basically what you have here is a sphere. Any strongly polarized, fully polarized signal will appear on the surface of the sphere. The full left-hand circular polarization is at the North Pole, right-hand circular polarization at the South Pole, and vertical to horizontal, in other words, linear polarization is around the equator. An unpolarized signal would be in the middle of this sphere. It wouldn't be on the surface at all. And if it's partially polarized, it'll be somewhere in between. So I hope you can see that in this particular case, and in fact in all the cases, this wave is completely on the surface. It has a coherent polarization the whole time. And there's a very clear home, if you like, and then some disturbances of various, and we've already heard about some of the reasons why those disturbances might happen, but it pings off into various directions and comes back generally. So let me go back to my PowerPoint slideshow again. Okay, so let's see if I can make it go good. So here's the signal from the Hungarian beacon on 6 different days, ranging from June through to late August here. And you can see that in each case, the blob was in a different place, but there is a blob. There is a sort of a home average rest state polarization. And it's on the right-hand circular half, it's on the southern hemisphere, and it's on the front of the sphere in this particular representation, which does actually correspond to the top right-hand quadrant in that on the ellipse representation. Here is Slovenia, and I get similar results, but much more chaotic on other beacons. These are, there's a clear home polarization, and it's in the northern hemisphere this time, so it's left-hand circular. These spheres are actually, because obviously this is two-dimensional, it's rotated front to back. So 3 out of the 4 are in the top left-hand quadrant. The ellipse is in the top left-hand quadrant. One of them is actually top right. So this is showing that there's a consistency here. And also, just for a matter of interest, the two right-hand spheres here, 18th of August and 20th of August, were taken on the same day as the last 2 of the Hungary records. In other words, it's not a systematic change in the equipment. So I then moved into rate-based modeling using FireLab. This is the 50 megahertz signal from Hungary. You can see that, well, first you can actually get a wave to land in roughly in the right place within 10 meters or something, using a reasonable level of ionization. The Sporadic E is not modeled in any of the tools, but I've added a Sporadic E layer at about 100 kilometers height, and with a plasma frequency, a critical frequency of just over 10 megahertz. It could have been a bit lower and still got a wave that landed there. And just for comparison, here's a pretend beacon, which there isn't, doesn't exist, on 7 megahertz, but the same path on 7 megahertz, which is a bit lower on the E layer. This is a 3D representation, by the way, because I had to use the 3D version of FireLab because it does separate X and O. But you can see how much smoother that flip over at the top is. It's not a right angle even then, to be honest, but it's a lot sharper than Sporadic E. So another thing you can do with FireLab is to look at the polarization of the wave. top left here. This is a slightly odd representation, I find. It's using the amplitude of polarization vector, which means that the O and the X ones are reciprocal of the other. But essentially, what we've got here is a wave. The characteristic wave on the way up, both of them are fairly close to circular, about 1.3, 1.4 axial ratio. As it crosses the Earth's magnetic field, as it is at 90 degrees to the magnetic field, it changes completely and then changes back again, or rather changes to the opposite polarizations. And down here, it's within 5% of circular. And one of the great things about ray tracing is it will actually do all the spherical geometry for you and tells you that the angle between the wave norm and the B field is more than 90 here and it's less than 90 there. Now, for the Slovenian part, something strange happens. And initially, I thought this was a mistake. I thought my model had blown up. But actually, what's happening here, and this is purely fortuitous, I can't claim any credit for this. It just so happens that this path skirts right along the 90 degrees. It's perpendicular to the Earth's magnetic field for a long time. Now, that's going to change the characteristic waves on the way up in the normal ionosphere, not the sporadic E layer. There's the sporadic E layer here. Whether this actually has much real effect, given that there's no deviation for wave. This is, as I said before, this is 50 megahertz. It's going pretty straight in the lower ionosphere. I don't know, but it's a very interesting pattern that, and this is work in progress, I should say. Interpreting this, taking this further is I appreciate some feedback actually, chaps, in terms of how I might take that forward. So conclusion so far. I think this is giving us convincing evidence, multiple paths, multiple events, that single hop of the strong kind, right, propagation at 50 megahertz is mainly magnetized. The ray trace modeling has given results for the home polarization state, which is reasonable. And what I'm doing at the moment is basically trying to predict the properties of the home state, and then we can worry about disturbances to it once we understand the home state. But it doesn't explain why the X and the O are not the same amplitude, because I can tell you they're not. So outstanding questions, particularly this first one: why are some beacons consistently right hand and others are consistently left? And then there's a lot more I can do in terms of modeling the shapes of the sporadic E patches and so on and so forth. So finally, back to that initial chart, and just to sort of annotate it with some points of learning, if you like, from what I've been doing. Firstly, there is there is a possibility that the coupling into the characteristic waves is not actually symmetrical. The polarizations change dramatically. I think there's a possibility of coupling between X and O up here, and then Parlap's quite good at predicting the range of phase differences that we see, but the absorption is not the answer because they're both very low and roughly the same, or very close to each other. That's it. Thank you very much.
Thank you so much, Chris. Appreciate it. Francis or Carl, are there any questions?
Fran, go ahead. You see any?
No, I don't see any at the moment.
I don't either. But I have a question, Chris. So I think we can rule out refraction because the sporadic E layer is so thin, right?
No, not at all. Because if it wasn't refraction, then the ray tracing wouldn't successfully predict it. I mean, if you look at the shape of the wave as it's inside the sporadic E layer, it's just being refracted very, very fast. It's an extremely steep ionization gradient.
Okay. So it's a very, very high electron density. So it doesn't need a lot of vertical extent to refract.
Yeah, I mean, the thickness does make a difference.
Yeah.
In that, the thicker it is, the more leeway it's got. If you see what I mean.
Okay.
But I can get a reflection in the model with a layer as thin as 1.5 kilometers.
Wonderful. Thank you.
Yeah, wonderful. That's right.
Thank you so much, Chris.
Yep.
Well, I find it interesting anyway.
And many other people do as well. I agree. Thank you so much.
So I need to stop. Oh no, I have stopped.
You're all set. So we have